Let's understand atomic structure in this video. Have you ever wondered what everything around you is made of? From your pencil to your pet. Everything you see, touch or smell is made of matter. And matter is made of tiny particles called atoms. Atoms are so small you cannot see them with the eye. A big question is, are atoms the smallest pieces or can we split them further? Long ago, thinkers in India and Greece asked similar questions about matter. Acharya Kannada in India called the smallest indivisible particles Parmanus, which combine to make dyads and triads. Greek philosophers like Leucippus and Democritus called these tiny particles atomos, meaning indivisible. These ancient ideas were mostly imagination, not experiments. But they started a long journey of wondering and testing. In 1808, John Dalton used experiments to make a scientific atomic theory and said matter is made of atoms, the basic building blocks. After Dalton, scientists asked what atoms are made of and how atoms of different elements differ. In 1897, J.J. Thomson discovered the electron by studying cathode rays in low-pressure gas tubes. He found tiny negatively charged particles called electrons, which are much lighter than atoms. Thomson took the electron charge as -1 by convention and showed electrons exist in all elements. To explain neutral atoms, Thomson suggested the plum pudding model, a positive sphere with electrons scattered like plums or seeds. But experiments later showed this model was not quite right. In 1911, Geiger and Marsden, under Rutherford, shot alpha particles at thin gold foil to test this idea. Alpha particles are tiny positive particles, like helium nuclei with 2 protons and 2 neutrons. Most alpha particles passed straight through the foil, but some bounced back or scattered at large angles. These surprising results meant the positive charge is not spread out but concentrated in a very small central nucleus. Rutherford proposed the nuclear model. Most of the atom is empty space, with a dense positively charged nucleus and electrons around it like planets. If the atom were the size of a cricket ground, the nucleus would be just a tiny pepper grain at the center. However, Rutherford's model had a problem. An electron moving in a circle should lose energy and spiral into the nucleus. But atoms are stable. Rutherford also showed the nucleus contains protons, each with charge +1. And protons are much heavier than electrons. To stay neutral, an atom has equal numbers of protons and electrons. In 1932, James Chadwick discovered the neutron, a neutral particle in the nucleus with mass like a proton. Neutrons add most of the mass to an atom and help hold protons together by the strong nuclear force. So, the main subatomic particles are electrons E- with charge -1, protons P+ with charge +1, and neutrons N with no charge. To explain atomic stability in spectra, Niels Bohr in 1913 proposed electrons move in fixed orbits or shells called K, L, M, N, or N equal to 1, 2, 3, 4. Each shell has a definite energy, and electrons do not lose energy while in a stationary state. Electrons can jump between shells by absorbing or emitting energy equal to the difference of the levels. The maximum number of electrons in a shell follows the rule 2n squared, spoken as 2n squared. So K shell n equals 1 can have 2 electrons, L shell n equals 2 can have 8, and M shell n equals 3 can have 18. Electrons fill shells from the one closest to the nucleus outward in the order K, L, M, N. The arrangement of electrons in shells is called the electronic configuration of an atom. The outermost shell is the valence shell, and its electrons are valence electrons, which decide how an atom combines with others. If the valence shell has 8 electrons, it is an octet, and the atom is usually stable, like noble gases. Valency is the number of electrons an atom gains, loses, or shares to complete its octet. For example, sodium has valency 1, oxygen valency 2, carbon valency 4. Atomic number symbol Z is the number of protons in the nucleus, and it defines the element. Mass number symbol A is the total number of protons and neutrons in the nucleus. So A equals Z plus number of neutrons. Standard notation writes mass number top left and atomic number bottom left of the element symbol. For example, 12,6C for carbon, 12,6C. John Dalton first used pictorial symbols. Then Berzelius suggested alphabetic symbols from Latin names. And today, IUPAC approves element names and symbols. Rule: the first letter of a symbol is capital, and the second, if any, is small. For example, Al for aluminium, Fe for iron. Not all atoms of an element have the same mass because of neutrons. These variants are called isotopes. Hydrogen has 3 isotopes: protium with 1 proton, deuterium with 1 proton and 1 neutron, and tritium with 1 proton and 2 neutrons. Isotopes have similar chemical behavior but different physical properties and uses, like carbon-14 for dating ancient things and cobalt-60 in cancer treatment. When different elements have the same mass number, they are called isobars. For example, 4020 Ca, 4019 K, and 4018 Ar all have mass number 40. To measure atomic masses, scientists use the Unified Atomic Mass Unit, written as U. For example, natural chlorine has about 75% 35U and 25% 37U, giving a weighted average of 35.5U. So what do we learn from this? We learn that atoms are made of a tiny, dense nucleus of protons and neutrons, with electrons in energy levels around it, and that atomic number and mass number tell us who we are. Let us quickly remember. Ancient ideas led to Dalton. Electrons were found by Thomson. Nucleus by Rutherford. Bohr gave energy levels, and Chadwick found the neutron. So today, we learned about atomic structure, subatomic particles, shells, valency, isotopes, isobars, and chemical symbols. Keep your curiosity alive and remember, science grows step by step by asking questions and testing ideas. Explore more lessons and practice examples on EduRev when you feel ready. There is no rush. Just enjoy learning. Thank you for listening. Keep wondering and see you in the next video.